Hello everybody and welcome to ECMath. Today we're going to look at section 3.5, which is all about growth and decay models. So if you ever wondered how long it would take for a population to reach its limit, how long it takes for something to freeze, how long a drug might stay in your bloodstream, or how long nuclear radiation might last floating through the air, then you are interested in exponential growth or decay models. The basic exponential growth and decay model looks like this. A equals A naught e to the k t. What are the pieces here? A is the amount after time. A naught is the initial amount. That zero is just a subscript there to say, it's the initial value. It's not actually a zero that does anything in the equation. E is E, the decimal number 2.71828, etc. You should use the E button on your calculator. K is what we call the growth constant. And I'll have more to say about K in a second. And then T is the number of time intervals. Sometimes that's years, sometimes that's weeks, days. It depends on the context of the problem, but it'll always be in a constant time interval within that problem. So let's talk more about this K, or growth constant. Because the K is really the sort of one new weird thing, and it actually has the greatest effect on the shape of the graph. If that K value in a model is positive, then you are looking at an exponential growth model. An example might be 3000 e to the 0.02 t. That's an example of a model that looks like exponential growth. And some people say, get this confused and say, well, 0.02 is less than 1. Isn't that decay? No, you're thinking about the old kind of model. In this new kind of model, we think about whether the K is positive or negative when we're deciding if something is growth or decay. If K is negative, that will be exponential decay, which is, a decreasing exponential quantity. Here's an example of an exponential decay. 200 e to the negative 0.16 t. That would be exponential decay. So exponential growth models will look like this, of course, and exponential decay models look something like, and this is, rough sketch, something like that. And those are the ways we tell them apart is by looking at that K value and whether it's positive or negative. If you remember the video where we talked about compound interest and continuous compounding, this formula should be familiar to you. In that video, we had A equals principal e to the RT, or PERT. This is the same structure in the formula, except when we're doing compounding, we thought about that as an interest rate or growth rate. Here, it's not technically really considered the growth rate. It's just a constant related, which is why we call it K and not R. But the structure of the formula is the same, and the way you work with them is pretty similar. Let's do an example. So in my kitchen, I noticed some fruit flies the other day, and I noticed 4 fruit flies. 2 days later, I went back in the kitchen hungry for a snack, and I noticed that there were 12 of these cute little suckers hanging out in my kitchen. Now imagine that there's no restrictions on food or anything else going on, and I don't do anything about my fruit fly problem because I'm too busy making videos. How many fruit flies would there be in 2 weeks? Well, it turns out we have all the information we need right here as long as we remember our growth model. So working up this given information, the initial population is 4. That's telling me A naught is 4. 2 days later, that's telling me when the time was 2 days, I found 12 fruit flies. Well, that's a final amount, so A would be 12. Well, let's plug all those into the model. So we could say 12 equals 4 e to the k times 2. The only thing we don't know is k. If we could find that k, then we could answer the second part of the question. So there's always going to be this hidden part of these problems where you have to find any missing parameters in the model and build the rest of the model. So we have 12 equals 4 e to the k2. That's an exponential equation. We can solve that just like we solved it in the last section. But to review the steps, let's see. We'll first divide by 4. So we get 3 equals e. I'm going to write this as 2k also, just to be tidier. Now, we want to express this in terms of a log. We need to get rid of this e. And like we did in the last section, the best move is to take the natural log of both sides. Natural log of e to the 2k is just 2k. Right? Those reduce out with each other, and you get equals natural log 3. So we've now put this in log form. We're almost solved for k. All we have to do is divide by 2. So we get that k is equal to, I should put it on this side, natural log of 3 divided by 2 is equal to k. And just to see what kind of model we're looking at, I'll get out my calculator. I can do natural log 3, close parentheses, divide by 2. And we're looking at a growth constant of about 0.54, let's say 0.55, which is what I might use, but I'm actually going to make sure I keep this value in the calculator. So I'd really recommend for this section having a calculator that can do natural logs, that can do e, and that has a memory where you can go up and get previous values. Those 3 things will really help you. Otherwise, you're going to be writing down a lot of things, and your answers won't be as precise. All right, so we know this k value now. We want to know how many fruit flies there will be in 2 weeks. Well, 2 weeks is 14 days. So to answer the second question, we need to rebuild the model. A equals, well, the initial amount was still 4. E, we now know k is 0.55, and t is now 14. Well, that's everything on one side. All that's left is to find a. So let's go to the calculator. Move that here so I can see it. So we're going to do 4. Get my mouse out so you can really see it. So I did 4. E to the x is right above natural log. And instead of typing in 0.55, I'm going to go get that value I had before. Use all the decimal places. That should be plenty of precision. Times 14. Hit enter. We get 8,747.99 fruit flies. I'm going to round that up to A equals 8,748 flies. Maybe one of them lost a leg somewhere. I don't know. Well, that's a lot of fruit flies. But they've been growing at this rate, which is not a small rate, for 14 whole days unchecked. Doesn't surprise me that I'm pretty much swamped with fruit flies right now. And that's how you solve this problem. You're always going to take your model, fill in all the blanks you can, solve for the missing parameters. Sometimes that's solving for k, sometimes that's solving for t. It depends on the problem. And then usually you have to plug it back in to find some new quantity or ask a second question. But none of the algebra here was really difficult. It's just knowing what to do and understanding the process. By the way, if you are thinking to yourself, Mr. Eck, this is really unrealistic. Populations don't usually grow unbounded. Populations usually, run out of food and maybe look like this after a while. You're right. And you want something called logistic growth, which is related to this. It actually uses the growth model as part of it, and we are going to cover that in another class. Not this video, it just would take a little bit too long, but this is kind of a simple model for population where there's no restriction on resources. Now it's time for a really cool problem. It's about water getting cold. So imagine that I put a pot of boiling water outside in the winter. Conveniently, the water was exactly 100 degrees Celsius when it was boiling, and the ambient outside temperature in the winter is, we'll say, exactly 0 degrees Celsius. So we're making some wild abstractions, and we're using Celsius because it makes all the numbers nicer today. It turns out, and this is something called Newton's law of cooling, that the way something cools, over time it's going to have an initial temperature, is going to be exponential decay, the way things cool. And we're doing right now a very simplified version of Newton's law of cooling because of this 0 here. That makes things a lot nicer. we can basically use our old exponential model, but this time instead of growth, it's going to be decay. So let's work this up. So this is kind of a weird problem because the amount is not the amount of water, it's actually the temperature of the water, or the two temperatures. So our initial amount is the 100 degrees. That's the initial amount. And 20 minutes later, the amount was 60 degrees. The time in that case was 20 minutes. And we don't know K, but we can plug these all into the model. And start to solve, and we're going to find the K for this situation. Make a little more room. So we can divide by 100. And simplify that fraction, so 6/10, that's 3 over 5, just to simplify that all the way, is equal to e to the 20k. Like before, the easiest move is to take the natural log of both sides. Natural log of e is just reduces with itself, so you get 20k, and that's equal to natural log of 3/5. To find k, we can just divide by 20. So k is natural log of 3/5 all over 20. Go back to our friend the calculator, see what that is. Close your parentheses, be sure you're doing all of that. So we get negative 0.025. I'm going to say negative 0.03 for what I write, but I'm going to use the entire value in my calculator for the calculation. All right, so we found K. Now I have to answer the question. When will the water be at 10 degrees? So let's take a look. All right, so we now have, in the second part of the problem, I'm finding something different. What's asking when, that's going to be solving for a t value, and it's giving me a different final amount. So my final amount is now going to be 10 degrees. My initial amount was still 100 degrees. My t is unknown, but my k is now known as negative 0.03. So let's plug all of that in the model. So we can divide by 100 and get 0.1 equals e to the negative 0.03 t. Take the natural log of both sides, so we get natural log of 0.1 equals negative 0.03 t. And we can do natural log of 0.1 divided by negative 0.03 should give us the t value. Let's go to the calculator. Now, I said negative 0.03, but I'm actually going to go up, and I'm just clicking the up key on the calculator to get that entire value and put that entirely down in there. And we get 90.15, so let's say approximately 90.2 minutes. So a couple interesting reflections here. First reflection is an error that I made. When I wrote this problem initially, I had asked, when will the water be at 0 degrees Celsius? And I solved this on my paper, and I got a negative time. I said, how can this be? And then I thought about it for a second, and I realized, oh, right, if we're doing exponential decay, the water will never actually reach 0 degrees Celsius. It's going to get very close. But this has to do with the physics of the situation. You've brought a cup of boiling water into a cold environment. That's added energy to the environment. That energy is going to go into the environment, and the environment will actually go, because the outside is very big and the water is very small, the environment will go up a little bit in temperature, just as the cup of boiling water really strongly decreases in temperature. So will it ever actually reach 0? No, because it secretly, incrementally warmed the environment up. It will get very close to 0, of course, but that's also why your freezer, to freeze water and make ice, actually has to go below 0 to make the ice work. Thing 2, If you think about freezing water very carefully, the freezing rate actually depends on a lot of factors. Mass of the water, like how much water you have, the surface area, is it spread out or is it all in one block? The type of container it's in, is it insulated, is it not? That actually will all affect the time, but all of that gets built into the K value. In that first step, we solved for K for a given situation, a certain vessel that the water was in and a certain height. And if I had a different vessel, I'd get a different K value and the answer would be different. But because we're solving it based on the data that was given in the problem, that's all built in when we find that K. So, you don't have to outthink this problem and account for all these variables if you have data that's there already. And if we have a little bit of extra time in class, we'll talk about the full version of Newton's law of cooling. It's not that different. It just has to have a way to take into account the ambient air temperature when it's not at zero and how the temperature can go close to the ambient temperature. It's really just a transformation, but for the sake of this video, we're going to keep it simple and not worry about that. So that might come next time. Let's look at another situation where you might use exponential growth or decay. Say you're walking around and you find a lovely scenic sinkhole full of radioactive ooze, and somehow you know that there are 1,200 gallons of ooze in that sinkhole. You also, from your previous research, know that the half-life of radioactive ooze is 10 weeks. You'd like to know how much ooze will be present after these time intervals down here at the bottom. Well, first we better talk about half-life and what that means. Half-life is the amount of time it takes for half of a given substance to disappear. And the reason that disappears might be different. If it's radioactive elements, they're actually giving off particles, so they're getting smaller. If it's water, it could be evaporation into the air. If it's drugs in your bloodstream, which is another thing that uses half-life, it could just be your body is processing that chemical and breaking it down. But we measure these all in units called half-life. And what's confusing for a lot of folks about half-life is that it is actually a unit of time. So the half-life for something is given in hours or minutes or seconds, depending on, of course, what the substance is. The other cool thing about half-life is it does not depend on amount. One huge sinkhole full of radioactive ooze will have the same half-life as one mug full of the same radioactive ooze. Because we're looking about proportions. We're thinking about half, not, specifically 5 ounces, but just half of the total. It doesn't matter how much you start with. It just matters how long it takes for half of it to remain. So now that we understand half-life, let's see if we can answer some of these questions. Well, let's first answer how much will be present after 0 weeks. Well, none has gone away, so there's going to be 1,200 gallons. After 10 weeks, well, the half-life of this is 10 weeks. So after those 10 weeks, exactly half of those 1,200 gallons will remain. That's 600 gallons. After 20 weeks, that's 10 more weeks. So half of the 600 will have disappeared again. Due to evaporation, radioactive decay, whatever, there's now going to be 300 gallons left. Oh, all right. Now 50 weeks. So let's see. We've skipped over a bunch. We've skipped over 30, 40, and then 50. So that's 3 half-lives down the line. So why don't we get our calculator out? So we're at 20 weeks and 300. Let's say divide by 2 again. That will be 30 weeks. There's 150. Divide by 2 again. At 40 weeks, there's 75. Divide by 2 again, because we've now gone 5 total half-lives, we'll have 37.5 gallons left. Now, if we were to just divide by 2 again, that would be 6 more half-lives, and that would be 60 weeks. and we'd have 18.75. But we were asked to find the amount after 55 weeks, which doesn't divide evenly into half of 1200. So how are we going to find it? Well, we need to make a model. But good news for us, we have all of this data right in front of us to work with. Okay, so we're going to use the same model we've always used. A equals A naught, always, for the duration of this video, A naught e to the kt, and let's use some stuff that we know. So I think the easiest data points to use will be these first 2 weeks. So we know the initial amount is 1200. We know that after 10 weeks, so we have k is still unknown times 10, we should get 600 remaining. And like before, we just have to solve for that k value. Now, an interesting thing is going to happen here. The first step is dividing by 1200. Now, 600 over 1200 is 1/2. And that would have happened no matter which 2 data points we chose. No, not those 2, but which data points we chose, as long as they were separated by 1/2 life, we would have just gotten 1/2 here. And that's what we meant when it said it didn't depend on the initial amount, because it's more about proportions and fractions reducing than it is about like actual volumes. So we would always get a half here no matter what initial condition we chose. We still need to solve this. Taking natural log of both sides is the best way. So we have natural log of 1/2 equals 10k. So then natural log of 1/2 over 10 should give you the k value. Which is approximately negative 0.07. And again, I'm going to use the exact value in the calculation, but we'll just mark it as that for now. So now I want to know how much will be present after 55 weeks. So I can say, okay, A equals initial amount was 1200, E to the negative 0.07 times the number of weeks, which was 55. Just going back in and using the standard model. Let's plug that in. Now I'm going to use the full decimal there, right? I'm going up and getting that full decimal times 55 for the weeks. We get about 26.52 gallons of radioactive slime. And that makes sense, or should make sense that it's somewhere between the numbers for 50 weeks and 60 weeks. So that seems like a good logical answer. And like before, we're just using our exponential growth or decay model and our calculators, but we have this idea of half-life built in. These problems using half-life and whether or not they use half-life can be confusing because of the way the information is sometimes presented in a problem. So say that a surgeon gives 200 milligrams of aspirin to a patient after a leg surgery. After 2 hours, they test the patient. There's 135 milligrams remaining in their bloodstream. And the surgeon would like to know, for future use, what is the half-life of the aspirin in the bloodstream? Well, if this had come out to exactly 100, we could just say, oh, the half-life was 2 hours, but it didn't. So we need to find the half-life, and to do that, we need to write a model. We need to use the data points we've got. So, like before, let's say A equals A naught e to the kt. In this case, 200 is going to be the initial amount. 2 hours will be the t, and 135 will be the final amount. Let's plug all that in. So we're going to solve for k. Divide by 200. Take natural log. That's kind of an icky k value, but it's still just a decimal. And, as we go, we should always be checking that we get negative values when we expect decay. So we're expecting this to decay out of the bloodstream. So I should be getting a negative 0.19 here as a pretty good logical value. So let's say negative, let's round to negative 0.2. But we're going to use the exact value like before. All right. Now, I want to know what is the half-life. So that feels like there's not enough information because it seems like I need to be solving for t. But I don't have any amounts. Well, here's the thing. We've talked about how half-life doesn't depend on the amount. It just depends on the growth constant and, the proportions. So just pick some amounts. Let's say that our initial amount was 200. Then the amount that we have that would be half would be exactly 100. And you just get to pick that because we're solving for half-life. We already know the k value. And we're trying to solve for t. So let's put this in. So 100 equals 200 e to the negative 0.2 t. And to find the half-life, we just need to solve for t. That t will represent the half-life because 100 is half of 200. Now, I divide by 200, I get this interesting thing again that says 1/2 equals e to the negative 0.2 t. And I get a feeling that I could have just started with an initial value of 1 and a final value of 1/2. That actually is the most efficient thing to do, is not even, don't go to the 200s. But if you don't like that, an initial value of 1 and a final value of half, you can pick any numbers you want. But let's go to the 1/2, take natural log of both sides, so we get natural log 1/2 equals negative 0.2 t, and divide by negative 0.2. Go to the calculator. Let's see what we get. Again, I'm using the full value in the calculator going up to get it. So that's about 3.57 hours. We are in hours, right? Yes. So the half-life of this substance is about 3.5 hours. So the final thing we want to talk about in this section is how to change the base of your model and express it with a base of E. The reason we might do this is that E is like a standardized base that everyone can use to compare growth or decay rates, so that when you publish a scientific paper and someone else over on the other side of the country publishes a different scientific paper, you don't have different log bases in it that are hard to compare. If we just all use base E or know how to convert things to base E, then we're all communicating in the same way, and that's really important. This is not the same as the change of base formula we talked about in section 3.3. There's still changing of bases, but this is not that formula. This is a new thing. And it just kind of compares the two exponential growth models that we've seen in the past. So here's to be concrete about it. Here are two models that, down to some rounding, have the exact same graph. 6 times 1.08 to the t, right? Exponential growth of roughly 8% per year. It's the 1.08, and that would look, something like this. And we also have 6e to the 0.077 t, also exponential growth because t is greater than 0, so that's going to be growth as well. And it turns out those have almost the exact same graph. Why do they do this? Well, I want to start with my calculator and the E-base model. Actually, let's look at the models as a total first. Let's look at what's the same. 6 is the same in both models. So is t. So the only thing that's sort of different between these models, let me get rid of this, is this 1.08 and this e to the 0.077. That's really the only difference between them. And I want to just compare how those are related. Well, I know what 1.08 is, but what about e to the 0.077? It's, like I said, down to rounding, that is 1.08. So this is approximately 1.08. And that e to the k takes the place of that growth rate b. So e to the k and b are intricately interconnected when we're switching bases. And there's a way to go between them. All right, so how do you do it? I like to just write the two models stacked on top of each other. So that's the yearly model, the old model. And here's our new model. Well, look at the parallel structure. A naught is A naught. T is T. The fact that this is multiplied here doesn't really change anything. You could also think about this as being raised to the t, because that's one of our little rules of exponents, right? Like, we don't really usually write it that way because it's not convenient. But we could think about this as e to the k to the t. So the t is in the same spot. The a naught is in the same spot. And so the only thing that must be, that to make these have the same graph, that must also be the same, is we must have, in a standard old model, the b needs to equal e to the k. And if we solve this for k, well, we could convert this to natural log form, and it would just be that natural log of b is equal to k. And that's how I did that other problem, actually. So in this problem, I started with a model of 6 times 1.08 to the t, and I said, okay, I need 1.08 to equal e to some k. I didn't know what 0.77 would be. So I said, okay, well, k is going to equal the natural log of b, putting it in the other form, which it was 1.08. And then I just did that. And I got about 0.769, which I rounded to 0.77. And that's why you saw when I went back in, it was slightly off, because I'd rounded to 0.77. And that's how you switch the base. So if I wanted to be a little more precise, I should have said natural log of 1.08. That would be the literal exact same graph. But this, if you go look it up in the book, is how you change from base B to a base E. If you have base B, well, then you know the B, and you need to find a K, so you take the natural log of B, that becomes your K. If you have a base E, you figure out what e to the k is, that becomes your new base, and everything else stays the same. So that's how you change the base. Let me give you an example. An iPhone loses about 30% of its value each year. That's called depreciation, and it is also something that behaves like an exponential decay model. If you've ever looked up the value of like an old iPhone, it's not zero, right? It's not expensive, but it's not zero because these things do hold their value. And, cars depreciate. A lot of things depreciate. I actually looked some of this up, and you can see, I didn't fit an exact curve, but you can see that it does go down by about 70% plus or minus, or it goes down by 30% every year, which means there's about 70% of the value remaining. And so you might have modeled this by saying, okay, 800 times 0.7, that is, 70% left to the t. But maybe you want to compare this with a friend across the country and they used base E. You want to see if their prices are the same as yours. Let's convert this to model to a base E. So we have, and I want to write this as 800 e to the k t. And again, I don't even need a fancy formula. I can, of course, use the formula that we wrote above, but you don't even need it. Ooh, not like that. You can just observe that to change this to base E, you need 0.7 to equal e to the k. Solve this for k. So natural log of 0.7 is equal to k. And compute what that is. About negative 0.36. And rewrite the model. So the new model would be A equals 800 e to the negative 0.36 t. And up to maybe some rounding error, these models should have the same graph, but one is in base E, which makes it easier to compare with other base E models. And that's how you do this parallel structure change of base. Again, it's not the change of base formula that you've read about earlier. It's more looking at and comparing the structure of AB to the X and AE to the KT. Well, folks, that's it. Thanks for sticking with me. I hope that these were interesting and engaging problems that kept you interested. Real-world problems can be difficult and messy, but they're real. They're something that actually is used. And exponential growth and decay is something that really is used in a lot of actual real situations. Please let me know what questions you have. Always do your homework, and I'll see you all next time.